Okay, so let's see, my recording. Okay. Who still needs to take the test? One, two. Are you doing it today or tomorrow? Today? Today? Okay. Um, because we still have, and I know there's a few others that aren't here yet that are scheduled to take it this week. Um, because of that, I'm not going to talk about the test because I don't want to give anybody any different information than everyone that took the test on Wednesday had. So with that said, please be patient. On Wednesday we'll talk about the test and everything else. Sound fair? Okay. So today is going to be pretty much our last day of lecture. On Wednesday, what we'll do is we'll talk about the final. We'll talk about the grades. We'll talk about the when is the final? Is it Wednesday? Yeah, it should be Wednesday. Yeah. So fortunately, you have a little bit of time to prepare for that final. All right. Um, we're gonna wrap up Cal 1 by starting to talk a little bit about, well, I mean, this is part of Cal 1, but I'm going to blend it into Cal 2, so there's a little bit of a transition, little overlap. So let me first motivate the idea, all right? In Cal 1, what we were interested in was taking a graph and then going to some point on that graph, let's say X, and figuring out what the slope of that tangent line was on that graph. And that was our derivative at that point. From that, we could figure out maximums, minimums, all those different sorts of things. We had to spend a lot of time figuring out how to take derivatives, right? We talked about, the different rules and power rule and product rule and quotient rule and chain rule, right? And I'm going to bite my lip to not talk about the test, and I'll just shut up, all right? But those are the most important skills from Cal 1, is being able to take derivatives and then geometrically what they mean. So in Cal 2, what we do is we learn that you can take a curve, and this time we'll look at it on a closed interval like this, and we'll be interested in trying to determine what the area below this curve is. All right? What the area of that is, which is very different geometrically than this picture is, right? And to do that, we will develop something called a Riemann sum, and I'll show you more of that later. But what it's going to turn out to be is that, like for this one, if you were given a function, if this was the function f, then to figure out the slope of this tangent line, you had to be able to figure out the derivative, right? Yes? Well, in Cal 2, what we learn is that if this is f, if you want to figure out what this area is, it's going to require you are able to come up with something called the antiderivative of f. In other words, you're going to have to find some function which I will call capital F, and that capital F has this property. The derivative of that capital F is that little f. Okay, so here, you start with f, you take its derivative. If you have that, you can figure out the slope of this tangent line. If you have f here and you want to find that area, you're going to have to be able to find a function that is the antiderivative of little f, meaning some function that when you take the derivative of it, you get this little f. So let me give you an example, a hard example, so you can see what I'm talking about. If I have, let's say, the graph of f equals x cubed, and I want to look between, let's say, 1 and 2, and I would like to figure out this area underneath this graph, right? I want to know that area. The way that I'm going to be able to do that is by determining what the capital F is, what the antiderivative of this is. So tell me, what do I take the derivative of to get x cubed? Well, think about it this way. When you take derivatives, what happens to powers? They come down, right? So I need to go from some power to x cubed, which means that it has to be what? X to the fourth, right? So I know it's got to be an x to the fourth, but that's not quite it, because if I take x to the fourth, I take its derivative, I get what? 4x cubed. I don't want the 4 to be there, right? So what I'm going to do is scale it by 1/4. Now it'll work, won't it? The derivative of this will be exactly x cubed, right? Or I could have used this one. How about this? 1/4 x to the fourth plus 1. That would have also worked, right? Because what's the derivative of this one? Same thing. Derivative of constant's still going to be 0. That's still x cubed, yes? But there turns out to be infinitely many, right? I could do this plus pi. Pi's a constant, right? I could do that. Or I could do minus 10. It doesn't matter, right? Do this all day long. Any of those would work, wouldn't they? So what we wind up doing is we say, why don't we just say it's this plus some constant? And that would cover all the possibilities, right? So that's what we're going to start. We're going to talk about the definition, what's an antiderivative, how do we find them, what are some of the rules that we have with them, and then I'll show you, how we can use them to find the area, all right? But right now, I just want you to make the connection that to do Cal 2, we actually have to be able to go backwards from what we were doing in Cal 1. In Cal 1, derivative is this direction. Cal 2, antiderivative is going backwards, which, as you might imagine, is much more difficult, right? Because think about something as simple as this. Let's say I give you a function. I don't know if this is the graph of it, but I don't know. I'm just making this up. If this is the function x sine x, that seems like a relatively simple function, right? I mean, it's not too bad, x sine x. I could ask you to take the derivative of it in Cal 1, and you would have to use what? Product rule, right? But in Cal 2, what do I take the derivative of to get that? What about that x in front, though? Yeah, so, I mean, you could start messing with things and be like, okay, maybe the x stays there, I don't know, and cosine, I don't know, square, I don't know what. Let me just say, it's not easy, all right? It's not this simple. And it especially won't be more simple, if I throw in there like x cubed or something like that, it becomes much more complicated. So what we have to do is we have to be able to have these ways of dealing with this. And so you spend the first several weeks, the first test is over just finding antiderivatives. That's all it's over. Who's taking Cal 2? So a good chunk of you. There's no, okay, you know how we have the product rule, quotient rule, chain rule? Okay, those are like what we consider shortcuts. But here's the thing about product rule, quotient rule, chain rule. They're very systematic, right? Like it's obvious with that it's a product rule. Yeah, it's obvious that that's a product rule. Okay, with antiderivatives, it's not as obvious. And so what we have are what we call the techniques of integration, but there's not like formula cookie cutter ways of doing it. It's just here's a technique, you try it, if it works, it works, if it doesn't, it doesn't. So it's much more difficult. Okay, Cal 2 is much more challenging because the backwards process is just harder. Undoing a chain rule is not easy, right? Undoing a product rule is not easy. And that's where most students struggle. So I would say that a majority of the students who do well in Cal 2 have got the differentiation down. Like they understand the product rule, the quotient rule, the chain rule. They've got that part down. If you struggle with derivatives, going backwards is going to be just, a nightmare. Okay, but let's just get to, what I want today to be about. and that's antiderivatives. All right. Capital F is called an antiderivative of little f if the derivative of capital F is little f. That's it. That's the definition of an antiderivative. An antiderivative of a function is a function that when you take its derivative, you get the function you started with. It's a very simple definition. As an example, if little f of x is equal to cosine x, then an antiderivative of that, capital F of x, is what? Not negative sine x. That's the derivative of cosine x, not what we're asking for. It's what? What do you take the derivative of to get cosine x? Sine x, right? Sine x? So capital F would be sine x. Is this the only one? Sine x plus 1, sine x minus 2, sine x plus c. How about that? So, but this is an antiderivative, isn't it? This is an antiderivative. That's why it says capital F is called an antiderivative of f if, as long as the derivative of it is f. So this is an antiderivative. And because there are infinitely many, what we have is what we call the general antiderivative. All right? The general antiderivative is capital F plus c. So this is a specific example. Here's another example. Another example. And then the last one I'll put here, capital F of x equals sine x plus capital C, which is any constant, right? C is any constant, is called the general antiderivative. The general antiderivative. Okay, that's your general antiderivative. Everyone understand the constant part of it? Yeah? Okay, now, let me write down an example, and we can talk about some language here. Find the general antiderivative of f of x equals 7. What's that? 7x? 7x plus c, right? 7x. So you're thinking, what do you take derivative of to get 7? Well, 7x, right? But plus any constant I want. So my answer here would be capital F of x equals 7x plus some constant. That's it. No, because I'm not taking a derivative, right? This is an antiderivative, which brings me to exactly why I'm showing this to you. If in Cal 1, if I give you a function in Cal 1 and I want you to find the derivative, all I say is what? Find f prime, right? Find f prime. Very easy for me to write that. Would you agree? In Cal 2, I'm trying to tell you, please find the antiderivative of a function. I am actually having to write out, find the general antiderivative of this function, right? There's got to be some other notation we use, right, to let you know to go find the antiderivative, right? So we definitely have notation for it, and here it is. All right, so now notation. if we want the general antiderivative of little f, we will write the following. Look at this as like an S that's been stretched out, an elongated S. And let me explain what everything in this is, all right? This is what we call the integral sign. Integral sign. The function that appears next to the integral sign is called the integrand. And this dx that's sitting here is called the differential. But all you need to know about it at this point in time is that this tells you the variable, the independent variable. Do you remember me telling you that story about how I used to go out and every once in a while get crazy, and then I always had like that question I would ask? I tell you all that story, remember? What's the derivative of x, right? And then most people say 1, but then if you said like with respect to what variable, that was like the great answer, right? Because when we said take the derivative, we always assumed x was the independent variable, but we also learned that at some points in time we needed to know what the independent variable was, right? So we would have to say like dy dx, so that you knew x was the variable. Well, with antiderivatives, it's the same way. We have to know what the variable is. And so the way we do it is by putting this little dx. D is like differential, like derivative kind of, it's dx. Normally dx is what? What's normally the derivative of x for us? What's that normally? 1, right? So this is like a 1, but it keeps track of what the variable is. Are y'all okay with that? So really, this is just part of the notation. It's not something you have to worry about in the problem, all right? Now, this integral sign right here, I'm going to show you why we use that sign, and if we have time today, I hope we can. And then this is just telling you what function you want to find the antiderivative of. Now, what we just said is that this, sorry, I kind of got in my own way there, will be equal to some capital F of x plus a constant, right? So capital F of x is our plus c is our antiderivative. This c right here is what's called the constant of integration. So here's what we've got. If you have a function, I'm going to try and give you a visual of this. Let's say I have a function f, and I tell you to take its derivative, right? That's called differentiation. Differentiation. Differentiation, right? The process of starting with a function and taking its derivative is called differentiation. If you instead start with the function and go back to some capital F, right, take its antiderivative, this is called integration. So that's a new technique, a new process. The process of taking the derivative of a function is called differentiation. The process of taking the antiderivative of a function is called integration. Make sense? Yay? Okay. So since this is called integration, that's why we call this the integral sign, integral integration. And then this is called the constant of integration because we will always have a constant of integration. Every time you find the general antiderivative of any function, you will always have a constant, always plus c. right? So it's called the constant of integration. It will always appear. All right? So with that notation, I'd like for us to look at this example. Find so how would I say that? There's a couple of ways I could say that. That's telling you to find the antiderivative of 5x to the 7th, right? Or it's telling you to integrate 5x to the 7th. Well, since it's a power function, right, since it's x to the 7th power, we know that it comes from something to the 8th power, right? It has to. It's just a matter of resolving the numbers so that when I take that 8 power out, I get what? I want that 8 that's going to come out when I differentiate it to be what? Turn into a 5, right? I don't want an 8 out there. I want a 5. So let's see if we can kind of think through this. I know I need this to be an x to the 8th. I know when that 8 comes out, I need it to kind of go away and become a 5. So what can I multiply it by? What can I divide it by so it's not there? Other way around. Divide it by 8, right? And the 8 that comes out will go away. And then multiply it by 5. So how about like this? 5 over 8. So what would happen? The 8 would come out, and then they would cancel with that 8 down there, right on the bottom. And all it would be left with is the 5. Yes? And then I say plus C, and I'm done. Does that seem straightforward? Let's do another one. Do I? And we're almost done. That's why. Okay, so we know that after we take the derivative, right, we need a negative 3 up there. So that means it had to come from a what? X to what power? Negative 2. Negative 2, right? Had to come from x to negative 2. Because when I bring the negative 2 down, it's going to take 1 away, it's going to be negative 3, right? And now I've got to make that in front become a 4. So what do I need to do here? Negative 2 on the bottom? That'll get rid of the negative 2, it's going to come down, right? But then you need what on top? 4, I think you were saying negative 2, right, already? But I'm just trying to follow the same pattern now, right? The negative 2 will come out. It will cancel out with that. And then the 4 would be left. And that would give you the 4x to negative 3. Plus C, we're done. Now, look at, did I really have to have that constant here? Like that 5, could I have just brought the 5 out of the integral sign, figured out the antiderivative of x to the 7th? What would the antiderivative of x to the 7th have been? It would be x to the 8th, and what would you have needed out front? 1/8, right? So you would have said 1/8 times x to the 5th, and then you would have brought the 5 back in, and it would have been 5/8. Same thing here. I could have brought the 4 out, found the antiderivative of this, which would have been just 1 over negative 2, x to negative 2, then brought the 4 in later. So it's just like what we had with derivatives. If you have a constant attached to the function, you can just bring it out. Do your antiderivative and then bring it back in. I'm just pointing that out, all right? So how about this? Maybe there's something that we can come up with to save us some time, a pattern we're noticing, that if you have x to any power, that will always do the same thing, no matter what. Let's see. What will we always have to do to that power? So in the antiderivative, we're going to add 1, right? Derivative, we always took away 1, right? So we're going to say whatever our x is, we're going to have to add 1 to that power. Agreed? And then we're going to have to multiply in front by what? 1 over n plus 1. See, 1 over n plus 1 is a number, isn't it? 1 over n plus 1 is a number. And when n plus 1 out here comes out, what will happen to it? It'll cancel out, and then we subtract 1 from the power, and we get our n. So, do you see this? Add a constant of integration onto it, and you have now created what is called the power rule. But not for derivatives, the power rule for what? For integration. So you know, sometimes as you learn things and you become more of an expert in different areas, you realize that the things you were saying in the past kind of shows people what you do and don't know. I don't know if you've ever had this experience in your real life, but like if you were to sit there and be talking to a calculus person and be like, oh yeah, you know, power rule. If they're like, yeah, I know what you're talking about, like, you know, n comes down, subtract 1, that means they haven't seen Cal 2, because there are actually 2 power rules. There's power rule for derivatives and power rule for integration. So when you just say power rule, it's too general. It's not enough. This is the one for integration. There's a different one for derivatives, right? The derivative one just says power down, subtract 1. That's derivative. Antiderivative, what? Add 1 to the power, multiply by 1 over that. Now, does anyone notice a value of n in which this would not work? That this formula would break down? If n's 0, it's okay. -1. Look, because what if n is -1? Look, you have -1, 1. What do you do then, right? So what I need to add here is this. At the bottom of this, just put for n not equal to -1. That rule will work. For any n, doesn't matter. As long as the n is not -1, that rule holds. So let's talk about what would happen if n was -1. Okay, let's talk about it. So what if you had integral x to the -1 dx? Somebody tell me what x to the -1 really is. I mean, another way I can write that. 1 over x. Right? Can anybody tell me what you take the derivative of to get 1 over x? Natural log. The natural log of x, right? So this should just be the natural log of x. Well, it's technically the absolute value of natural log of x, because you can't take the log of a negative number, so we always put an absolute value around it. If you look it up as a formula in a book, this is the way it will appear. But does that make sense? The derivative of natural log of x is 1 over x. So the antiderivative of 1 over x is natural log of x plus a constant of integration. So what we have now, if we combine these two together, this is for n equals -1. We have a way of finding the antiderivative of any power of x. Anything. Doesn't matter what it is. The special case that n is -1, it's always going to be natural log. Any other value of n, it's going to be that formula. You buy it? Let's see. Find the antiderivative of 5 over the cube root of x squared. Well, here's the thing. I have to be able to, right now, the only thing we know how to integrate at this point is a power, x to a power, right? So I could rewrite this like this. That's really x to what power down there? 2/3, right? dx. Now, do you think that when it comes to finding antiderivatives, that if I have a fraction, a quotient, that if I want to find the antiderivative, I just do antiderivative of the top and then antiderivative of the bottom? Hell no, right? I mean, when we wanted the derivative of a quotient, it was a mess, wasn't it? It was like f prime g minus g prime f all over g squared. So you have to imagine that the antiderivative could not possibly be just the antiderivative top and bottom, and that is correct. It is not. So what you would not do here is say, oh, I can figure out the antiderivative of 5 and then the antiderivative of this, and then just go work those out separately. No. You have to be able to write this right now as x to a power. It's the only thing we know how to do. So bring the x up. Bring it out of the denominator. This turns into what? 5x to the negative 2/3. We're not worried about the fact that it's negative, okay? Because our formula can handle anything, right? Any power. Even -1 it can handle. Now this time I am going to take that 5 out because 5 is a constant. I will bring it out of the integral like that. It'll be multiplied in front. And then I will do x to the 2/3 dx. Negative, thank you. And then apply the rule. So for us, what's n? Negative 2/3, right? N is equal to negative 2/3. So what's n plus 1? Negative 2/3 plus 1 is 1/3, isn't it? Negative 2/3 plus 1 is 1/3. So what I need to do is I need to rewrite this as now what? 5, right? Now I'm actually taking the antiderivative, right? So no more integral sign because I'm going to apply the rule. It'll be 1 over n plus 1. What was n plus 1? 1/3. So it's 1 over 1/3. Yes, that will flip up and become a 3, okay? But I'm just writing it out as the formula says I should. Then it'll be x to what power? 1/3. And then plus c. Now, everybody always asks me when they're seeing this for the first time, they're like, what happens to the dx? Like, where's the dx? And my answer to you at this point is that, again, the dx just tells you what variable you are treating, what letter you're treating as your variable, okay? Like, what's the variable in the problem? What are you integrating? I can give you a good example of what I mean by this. I think I can. I guess not. Well, this was today in my Cal class, my Cal 3 class. So what we have is what's called a double integral, which will come later. But look at the inside integral. It goes from 0 to 2 pi, which don't even worry about these numbers yet. But see the integral sign? And then you see all this mess in here? This mess in here is all that, okay? Notice I have two variables in here, u and v. Do you see that? So this dv right here at the end tells me I'm first going to find the antiderivative treating my v like the variable, and that means the u's I will treat like a constant. All right, just like when we did derivatives in here, right? Sometimes we treated things like constants, sometimes we didn't. And then what happens is you do all that, and then later, after whatever you get for that answer, then you come through, and then you treat u like your variable. So that little thing just keeps track of what's the variable and what's not. Understand? Yeah, are you just being agreeable? Yeah? Yeah. All right. It just keeps track, that's it. I mean, for us, x is the only thing we're going to see, so it doesn't, why do we need it? Well, we need it later, all right? And we're going to need it later in this class too, like, well, maybe. In the beginning of Cal 2, you'll need it. So look, that just keeps track. So as soon as you take the antiderivative, as soon as you actually apply the rule, it's gone. No more dx, it's gone. It goes away with the integral sign, right? The integral sign goes away, and so does the dx. Both those things are going to vanish from the problem completely as soon as you apply the rule, all right? It's kind of like when you took a limit. At some point, the limit went away, right? And you actually had your answer. When you take the antiderivative, the integral sign, the dx go away, you get this. Now, I have to clean that up because I'm not happy with that. This is the same as what? 15x to the 1/3 plus c. Questions? Comments? Concerns? I wonder if we can come up with the formula real quick for something. Yes. Yep. Not today, not in this class. In Cal 2 it will. See, I mean, let me try and just motivate, because I like your questions. You always ask good questions. Do you remember that if we had a function d that gave us distance versus time, like a position function, then if we took the derivative of it, it gave us what? Velocity, right? And if we took the derivative of the velocity, what did it give us? Acceleration. Remember that? So guess what? If somebody gives me an acceleration function, then I'm going to be able to go backwards to get the velocity function, right? But I'm going to be off by a constant. I'm within a constant of the true velocity function. So in the problem, what they'll do is they'll give you something called an initial condition, and it allows you to actually solve for that c. And then once you have that c, you have the exact velocity function. You go backwards again, and you get your distance. And that will again have its own c, and they'll give you in the problem another initial condition. You'll be able to get that c. So for us right now, no, it's just a c. Later on, we will want to know that c. All right? Okay, so let's go back to this. What is the antiderivative of a constant? Now, I don't want to use c because c is like our constant of integration. So I'm going to say k dx. Where k is a constant. You've already done a couple of these for me. What's the derivative of a constant? The derivative. 0, right? But antiderivative is the other way. So what's the antiderivative of 7? We did this earlier. It was 7x, right? Plus a constant. What's the antiderivative of 10? 10x. What's the antiderivative of pi? What's the antiderivative of e? Not to the x, just ex, right? If it's a number and I want to find the antiderivative of a number, all I do is take that number and slap an x next to it, right? That's it. This will just be kx plus what? A constant of integration, which is going to be something else. Now, notice, that's a constant by itself. The antiderivative is kx. Up here, that 5 that was with us, right? It came out, right? That 5 came out and then came back in. I did not have to take the antiderivative of 5. Why? Because it was attached to a function of x. Just like when you take the derivative of something with the constant, right? In the function, you take derivative of the function, you leave the constant there. Yay or nay? Derivative of 5 sine x is what? 5 cosine x. You leave the 5 alone because you're going to take derivative of the sine part. What's derivative of 5 by itself? 0. All right? So that's, two different situations. All right, let's try this one. By the way, this is stuff. This will be on the final. We're not just having fun today. Yeah, this is this is Cal 1 material. This is Cal 1 material. Antiderivatives is Cal 1 material. I'm just saying it is this is the beginning of Cal 2. Most instructors will start with this. The fact that you see it now will benefit you. All right? Yes. We're going to talk about the final next class. Yep. All right. What do you think? Do you think you can just say, oh, I can find the antiderivative of 10 and then the antiderivative of 3x? No, because the squared, right? So the only hope we have here is to actually multiply that out, like FOIL it out. Won't this become 100 minus 60x plus 9x squared dx? Yes? If you multiply that all out, let's FOIL it, right? Okay, now, when it came to derivatives, when you had the derivative of a bunch of things being added or subtracted together, didn't you just do the derivative of each one and add and subtract the answers? Do you think it works the same way for antiderivatives? Yes, it does. Thank goodness. That's the only thing that works the same way. All right? If you have sums and differences between terms, you can split this into separate integrals. Now, we don't like to do that because it's just more writing. So what we do is mentally, we take the antiderivative of each term separately. Okay? So let's see if you can keep up with this. What is the antiderivative of 100? 100x. Notice no more integral sign, right? No more integral sign, so I'm actually taking the antiderivative. What is the antiderivative of negative 60x? So negative 60, right? Divide that by what? 2, and then x squared, right? That's this one. So I left the negative 60 here. I'm dividing by 2. I'm raising to the 2. Now, look, you will get to a point where you just look at that and you're like negative 30x squared. But I'm just showing you the detail, all right? What's the next one going to be? Plus the 9 stays over 3x to the third. Plus a constant of integration. Dx is gone, right? And now you would just clean this up. 100x minus 30x squared plus 3x cubed plus c. Box it up. You're done. Questions? One more, and then we're going to move on to one more idea that we have in this topic. How about this? It's looking uglier and uglier, isn't it? Can you or can you not? You'd say yes? No. I'll say yes. You can. I mean, algebraically, right? If you have multiple terms on top and a single term on the bottom, you can break it up into separate, right? Now, what is the danger I see, the thing I see students do? They just say, okay, look, all of these are powers of x, and they just take the antiderivative of everything. So they're like, okay, antiderivative of this is 4x, right? It's 4x, and then they figure out what this one is, and this one's like 3 halves x squared, and they figure out this one's like negative 4/3 x cubed, and they say, oh, and this one's 1/3 x cubed. And they do it, they just write it all like that with a fraction. You can't do that because it's a fraction. You have to be able, the only way you can use the rule is if it's just powers of x by themselves without fractions. Are you with me or not? But I can split it up, so I will do that. This is the same as 4 over x squared minus root x over x squared plus 3x over x squared minus 4x squared over x squared dx. And now each of those, I need to turn those into powers of x. I am not taking an antiderivative yet. The first one is what? 4x to the negative 2. What is this? That's x to the 1/2 over x to the 2, which is x to the 1/2 minus 2, which is x to the negative 3/2. Right? Square root of x is x to the 1/2. X to the 1/2 over x squared is x to the 1/2 minus 2. 1/2 minus 2 is negative 3/2, so that's x to the negative 3/2. Yeah? So this right here becomes minus, because it was a minus there, x to the negative 3/2. What about this next one? 3x over x squared becomes what? 3x to the negative 1, right? But wasn't the negative 1 that special case? Wasn't it? So I'm actually going to leave this as 3 times 1 over x, because I'm thinking ahead that I already know that 1 over x is the special one that gives me natural log, isn't it, when I take the antiderivative? So I'm going to leave it like that instead. And then the last one is what? Minus just 4, right? The x squareds cancel, dx. Now you have 1, 2, 3, 4 terms, right? 4 terms. I can take the antiderivative term by term. Here we go. No more integral sign. Dx is going to go away. Antiderivative of 4 attached to x to the negative 2 is 4 over what? Negative 1 x to the negative 1. The most common things that I see at this point is, like I heard, negative 3. You start thinking still kind of in the differentiation mode. Right? You're adding this time. Okay, so the next one is minus, 1 over, what's n plus 1? Yes, so this is n, right? That's n. What's negative 3/2 plus 1? Negative 1/2. Negative 1/2. So you get 1 over negative 1/2, and then x to the negative 1/2. What about the next one? Plus, what do I do with this 3? Just leave it. Antiderivative of 1 over x, natural log. 3 natural log absolute value of x. Always absolute value on the antiderivative here. Say that? What's the antiderivative of negative 4, though, or negative 4x? We're going to say plus c at the very end. Yeah. Minus 4x, and then now constant of integration. And we're done. Now we need to clean this up because this looks nasty. Are there any questions on where any of that came from, though? No? What does this first one turn into? Negative 4 over x. I could write it that way. Negative 4 over x. I'm out of room. I'll put it right over here. Negative 4 over x. You could leave it negative 4x to the negative 1. You could, especially if you have to take the antiderivative again. You'd want it to be written as a power. What about the next one? 2. So this is positive 2, right, in the front. And then this is the same as 1 over square root of x. So 2 over root x, positive 2 over root x. And then plus 3 natural log x minus 4x plus a constant. Make sense? At this point, I've covered the basic part of antiderivatives that I want to cover. I'd like to just test the waters here to see how you feel about what would be the next step in integration, all right? Right now, we can pretty much handle any power of x, right? Any power of x. We could also handle things like antiderivative of cosine, right? Antiderivative of cosine should be sine. What's the antiderivative of sine? Antiderivative of cosine x we just said was sine x. That made sense, sine x plus c. Antiderivative of sine x is negative cosine x, because you have to account for the fact that the derivative of cosine of x is negative sine x. So you put a negative in front to make that negative become positive. Yes? And there are a lot of these that we can do. There's a lot we can't do. Like, could you do the antiderivative of secant squared x? What do you take the derivative of to get secant squared? Tangent. Right? But something as simple as this, by itself, not so easy. This is not something we're going to be able to think of. So go back to what we learned in Cal 1. We're in Cal 1 still. Okay, what's the derivative? What is the derivative of sine? Cosine, so the antiderivative of cosine should be sine. What's the derivative of cosine? Negative sine, right? So the antiderivative of negative sine should be cosine. So we can do anything we knew the derivative of, we can go backwards now, right? But if it's something we didn't know where it came from, we can't go backwards, right? The derivative of what is secant x? Oh, I don't know. Right? Not going to be able to figure it out easily. So there's question marks here. That's not what I wanted to show you. I just wanted to say that anything that we knew trig-wise, we can go backwards from, right? But there are a lot of things we won't be able to go backwards from at this point. So in the natural progression of things, the next thing that we would do is introduce you to something called substitution. Excuse me. Try that again. Okay. I accidentally touched the button and turned it off. Okay, so when it comes to integration, there's the power rule for integration, which we've seen, right? The next technique that you learn is called substitution. After substitution is integration by parts. After integration by parts is trig integrals, then trigonometric substitution, then partial fraction decomposition. Those are your techniques of integration. All right? So I plan to show you the power we've got. The substitution you will see again for sure in Cal 2. But I assure you that this method, I mean, this technique right here is kind of like, it's equivalent to, I don't know. Let me just show it to you. You tell me what you think of it, all right? Okay, look, let's go to this. Let's go back to this one that we had earlier. It was 10 minus 3x squared dx, right? Remember that? We had that a second ago? Yeah? Now, I'm going to make a substitution right now. I'll explain why I'm doing it in a minute, and hopefully you'll start to catch on. I would like you to please, everywhere you see 10 minus 3x, I would like for you to replace it, please, with a u. Yeah, like college algebra. That's all I'm doing, all right? So let's rewrite this integral. It'll be the integral, which is saying I want the antiderivative of. Then it'll be what? This is now going to be a u, so that'll be u squared. Now here's where the dx starts to become an issue. The dx told us what our variable was, right? But what's our variable now? It's u. I need to switch dx to become a du, but I can't just switch it. I have to keep the relationship between u and x together. So what I'm going to do is on the left side of this equation, see this substitution? What I'm going to do is I'm going to take the derivative on both sides of this equation with respect to x. Okay, so watch this. What is the derivative of the left side? Du dx. I'm using Leibniz notation. What's the derivative of the right side with respect to x? Derivative of 10 is 0. Derivative of negative 3x is negative 3. Yes? Do you see this little new equation that I got from differentiating both sides? Do you see that it has a du in it? Yes? Yeah? Do you see it has a dx in it? Do you see I'm trying to go from dx to du? Watch what I do now. du is equal to negative 3 dx. Do you agree? Treating it almost like a fraction on the left side, multiplying both sides by dx. Can you solve this for dx now? Divide both sides by negative 3. So doesn't that give you negative 1/3 du equals dx? You with me there? So what I'm going to do is this. This dx is going to replace that dx. So I'm replacing dx in that integral with what? Times, so this is like multiplication right here, times what? Negative 1/3 du. So this became this, right? And this became that. Do y'all see that? Do I really need those lines? No, I don't need those lines. This became this. And this part became just that part. Do y'all see it? Now, let me clean this integral up. This new integral becomes what? What can I do with the negative 1/3? It's a constant, right? Can I pull it out of the integral completely? Negative 1/3 integral, what's still there? U squared du. Oh, by the way, you can never pull a variable out of an integral, okay? Because it's part of what you're trying to integrate. Only constants can come out, or things that would not be affected by u. So like in Cal 3 or something, if there was a v in there, you could pull the v out. Okay, now you're back to something to a power, right? This may as well say x squared dx, right? But we're in terms of u now. So use the power rule on that. So I'm about to say the antiderivative is what? Negative 1/3 stays there, times, no more integral sign. What? 1/3? U to the third? Let's see, thank you. Okay, so look, I'm not a big, like, I don't get all pissed off at my Cal 2 classes when they forget C. But there are professors at colleges all over the country that will count the problem wrong if you forget the constant of integration. I mean, to some people it's that important. So for me, not that big of a deal, but I'm going to show it to you, not knowing who you're going to take for Cal 2. Do not forget your constant of integration. When you integrate, you always have a constant of integration. Okay, now we can put that together. This is going to be what? Negative 1/9? U cubed? Yes? Now, your answer, although I agree, plus C, although your answer is you're almost there, we made a substitution, didn't we? We must substitute back. And this is the place to do it. So switching back, I'm going to replace u now with whatever we had. What was u? 10 minus 3x, but now to the third plus c. Is that the answer we got earlier? We did this problem earlier, didn't we? That was it right there, right? I would argue, and I think you might agree with me, that this was easier to do it this way. Would you agree? Because all we did was just spoiled it out and then just did it and it was done, right? How in the hell is that the same answer as what we just got, right? Well, is it? Yes. I'm not going to do it, but if we actually multiply this out, so cube it, then and then distribute a negative 1/9 through it, you would get the same exact answer, right? Do you believe it or not? Oh, I'm not going to do it by hand. I'm going to have Mathematica do it. Expand. I didn't show you a lot of Mathematica, did I, this semester? Expand, what was it, 10 minus 3x cubed, but then it was times negative 1/9? Okay, so this is what we have. Did we have 100x minus 30x squared plus 3x cubed? Okay, but I also got this here, right? Does that matter? No, because it's plus c. It doesn't matter if I'm off by a constant or not. We're all off by a constant. It doesn't matter. Okay? Y'all understand that? Now, so you may say, look, why would you do this, all this, if you could have done it the other way, right? Because what about, yeah, exactly. What if it was this? See, now you don't want to go that direction, do you? But look, this is the same setup. What's the only difference? Negative 1/3. It would all still work the same way, but this would be u to the what instead? 100. And that we're not worried about. Okay, the dot, dot, dot means you would still make the substitution. U is 10 minus 3x. You would solve for du or dx. You do all that, and you would just be replacing your u, right? The negative 1/3 would come out. So everything is exactly the same. The only difference is that's u to the 100. That means your antiderivative would be what? 1 over 101? U to the 101 plus c? You see that? And so, I mean, that, I have an answer. Nobody would be able to do this by hand, okay? No one. 10 minus 3x to the 100th power. Good night. I said no one. I don't consider my computer a person. But there's the expansion right there of 10 minus 3x to the 100th power. Right? This is pretty cool. Mathematica has this ability here where I can sit here and I can control. So this is 10 minus 3x to the first power. Here it is squared, cubed, fourth, fifth, sixth, seventh. So I can control the n. That's pretty cool, huh? All right, off topic. All right, so let's look at something else, all right? Make that cosine. I'll take it easy on you. Is everyone still in a turkey coma today, or everyone had time to recover? Now, we can throw out the power rule completely here because we don't have just x to a power, right? I mean, we do have an x to a power here, but it's stuck with this 1. It's trapped in a cosine. And then this x right here is to a power. Great, yes, but it's being multiplied times something, not added. So it's not something we can easily do, right? So in the last problem I said, let's make a substitution. I didn't really tell you why I made the substitution. I just did it, didn't I? Now I want you to think a little bit more about why I did the substitution. So look in this problem right here. Here's the idea behind substitution. Do you see something and its derivative? Or do you see something and something close to its derivative? Maybe off by a number? Remember I said Cal 2 antiderivatives, Cal 1 walking forward, Cal 2 walking backwards. People who do well in Cal 1 usually do like really well in Cal 1 can take derivatives, do well with antiderivatives because they can see it. They can see it already. Like not the whole answer, but do you see something and its derivative? anything and its derivative. Two separate things. Cosine, but the derivative of cosine would have signs in it. I don't see any signs anywhere. X and what? X squared. So what you're saying that you see something being the x squared and you see its derivative as being x, kind of close? Do you all agree with that? If I look at x squared, what's the derivative of x squared? 2x. Do I have a 2x sitting out here? Not really, right? But it's close. It's an x. Okay, so why not even go with the plus 1 also, right? How about x squared plus 1? Do you see what's the derivative of x squared plus 1? Still 2x, right? So at some point I have to kind of choose a u. I have to go for it. Try something. So what you want to do is grab enough to make a difference in the problem, but not so much you can't do it. And you only get, you have to see it and practice it. Let me show you. I'm going to let u be equal to x squared plus 1. The reason I did not do just x squared was because doing x squared plus 1 does not change what I get when I take the derivative, right? It's the same exact derivative. So what that means is I will be able to replace this x squared plus 1 with what? What will I be able to swap that out with? A u, which will be nice, cosine u. That looks great, right? But it's the x part in the front that's a problem. So what I'm going to do now is what I did before. I'm going to take the derivative on both sides with respect to x over here on the right. I get du dx is what? $2x, right? Everyone's what? Oh, don't. Why? That's why we're here. Multiply both sides by dx. All right. Okay, so now, hold on a second. There are different approaches to this by different instructors, and this will depend, if you take Cal 2, how they approach it. Here's the way I like to approach it. I like to see what I have over here and try and make this match it, right? So look. I have an x, right? And I have a dx. That's the only part of this that's not resolved. Can you go walk around, go get some fresh air, come back? Or if you're too tired, you can go home. But no one's going to sleep today. All right? That sound fair? Okay. So I'm looking at x dx, right? I have an x dx over here, don't I? I have x dx right there. So what I'm going to do is I want to be able to replace that x dx up there with this x dx here, but I have a 2 there, so how can I get rid of the 2? Just bring it to the other side as 1/2, yes? So I can rewrite this as 1/2 du is equal to x dx. Yeah? Yes. Ah, great question. Okay, so let me write this. This is the same as x times, now cosine x squared plus 1 is not multiplication, right? Like we are not saying this is cos times this parentheses, right? It's cosine of. So that's this, and then I have times dx. Now multiplication is commutative, meaning I can slide things around. So this is the same as cosine x squared plus 1 times x times dx, right? Which is the same as x dx, right? So this right here is going to match up exactly with that piece right there. You do not have to rewrite it if you're going to do it, no, but if you need to kind of help yourself, a lot of my Cal 2 students in the beginning, they will rewrite it exactly so that they can see exactly what it is they're going to be replacing. And some of them don't. Some of them just see it and they do it. All right, so I'm going to replace my x dx with what? 1/2 du, and I'm going to replace my x squared plus 1 with what? U. And the cosine doesn't get replaced. It just stays there, right? So this is going to become a new integral. I like to put an arrow for a new integral because it's not exactly the same because I've changed the variables. So my new integral becomes cosine u times what's x dx? 1/2 du. Now everything's in terms of u, right? So I pull the 1/2 out to the front, cosine u du. I don't need the parentheses around the u. What is the antiderivative of cosine u? Sine u, right? Careful. That's going to take a while to get used to. The antiderivative of cosine u is sine u. So the 1/2 in front, sine u, then plus c, all right? And now let's switch it back. What? Question, Tim? No? Antiderivative of cosine, right? Integral sign goes away. Antiderivative of cosine u is sine u. 1/2's out front, plus our constant of integration. And now replace u now with what u is. What's u? So 1/2 sine x squared plus 1 plus a c. Now there is some good news. You can always check your answer. Because the derivative of that should be what? X cosine x squared plus 1, right? So how would we take the derivative of this? Just to check our answer. 1/2, cover it up. What's derivative of sine of something? Cosine of that something, okay? Times the derivative of what's inside. What's the derivative of what's inside? 2x. What's half of 2x? X. So that would be x cosine x squared plus 1. That would work, wouldn't it? Do you see what I mean by seeing it backwards in like the derivative of this is that? But there's no one's, until you get really good at this, no one's going to see it right off the bat. So what you do is start trying to see these little things that are happening. I see something and I see its derivative kind of. So I try it. Right? Let me see what I have in here that I don't feel like I want to push much further. So let's do one more. Just one more. I'm not going to be done for the day, though, please understand. All right? We're not going to cut out early or anything. This will be the last thing that will be tested, okay? Pardon me? Okay, so you're wanting to bring this x up as an x to negative 1? Okay, that's one thought here. I'm not saying it's wrong. Any other ideas? What do you want to do? Like when you say substitute natural, you mean let u be natural log of x? Okay. Nope. Mm-mm. Okay, so let me ask about the substitution of u as natural log of x. Is there any particular reason why? What's the derivative of natural log of x? Do you have 1 over x there? Yes, you do. Okay, so what you have to realize here is that this is the same as natural log of x to the 7th power times 1/4 times 1 over x dx. Isn't that exactly the same thing? Now, the 1/4 doesn't matter, does it? I mean, that can come out. And so, yes, you do see something and its derivative, don't you? Now you see it, hopefully. Yes? Yes? Yeah, but it was a good guess, and that's part of it, okay? That is part of Cal 2, is that you have to take a swing. You have to take a swing at it. It's not like Cal 1 where it's like product rule, monkey see, monkey do, product rule, f prime g plus g prime f. It's not that. It is really, you have to try something. Substitution, you try it. You make one, right? Now, you would have brought the x to the 1 up. You would have run into some problems there because they're attached to each other by multiplication, so you can't use power rule. All right, so let's pull the 1/4 out because I don't like it. And maybe I shouldn't have done that because that's me, I guess, knowing too much ahead that I'm not going to need it. So if you wanted to, you could leave it in there. Okay, so you're going to make your substitution, right? You chose to let u be equal to natural log x. You did that because du dx was what? 1 over x, right? And then du would then be 1 over x dx. And because of the way things worked out, 1 over x dx is exactly sitting here, isn't it? How wonderful is that? That right there happens to be exactly this. I won't even need to touch it. This exactly will be replaced with what? Du. And then the natural log x inside, which we made a substitution of, is going to become what? U. That's right. You're making a substitution, so you're turning one integral into one that's easier. So this will become 1/4 integral what? U to the 7th du. U to the 7th du. What is the antiderivative of u to the 7th? 1 over 8 u to the 8th. Plus c, thank you. Which is 1/32 u to the 8th. What's u? ln x to the 8th plus c. Done. If you checked your answer, it would work because you would first, this is chain rule, right? Derivative of this, the 8 would come down, make that a 1/4. So you have 1/4 natural log x to the 7th. Then you go inside, take derivative natural log of x, 1 over x. So you have 1/4 times natural log x to the 7th times 1 over x. Squish them all back together, it's going to be natural log x to the 7th over 4x. Yeah? Okay. I think that's as far as I'll take it. Like I said, you'll start out with substitution in Cal 2 if you're taking Cal 2. I would like, if I could, to just spend the rest of today talking about something I'm not sure you'll see in Cal 2. It'll depend on your instructor. Some instructors just get right into the antiderivative and never really explain anything about, well, just let me shut up and just talk. All right, let me show you. But please, out of respect for this being my last real 20 minutes of talking, at least don't like just sit there, start texting and sleeping. I mean, you know, I think this is valuable information. So if you were to say, I mean, why do we want the area under a curve, right? I mean, why do you want it? So let's say you have time and distance again. Or no, let's say speed. velocity. So I'm driving down the road, right? I start the clock, let's say at 1 hour, and then let's say 4 hours later. What I can do is that at 1 hour, I start looking down at my speedometer, right, and I have a speed. That's my velocity. And at every moment in time, for the whole trip, I have a speed. Yes? The entire time. What does the area under the curve represent? Total displacement. How far I went. Because what it is it's your speed at every moment, right? What you're doing is you're adding up all of these speeds over the entire time interval. What is speed? Speed is distance over time. What the hell is that noise? So distance is speed. What is that noise? Do y'all hear it? It's irritating. Distance. I just hear something like weird. Okay, if speed is distance over time, then distance is speed times time, right? So imagine, if you could, me taking like a rectangle right here. What's the area of that rectangle? Well, I'm going to blow up that rectangle real big. Do you agree that this width is a measurement of time? And do you agree that the height is our measurement of speed? So do you agree the area of that rectangle is time times speed? And so that should represent a distance over that little slot of time, right? So what I could do if I really wanted to kind of get an average idea of what my distance was, is I could cut this into a bunch of rectangles, right? And try and figure it out. Yes? And that would give me an approximation, wouldn't it? That would get me kind of close to the answer. I'm going to show you a little more, but I wanted to do something other than velocity and time. How about if this was time and force? Or you know what? Distance. So what was velocity times time? It was speed, right? What's force times distance? Force times displacement. So I'm multiplying. Do y'all see that what I'm doing? When you're looking at the area under a curve, what you're really doing is taking this and multiplying by that and trying to figure out what the hell that means. Like velocity times time is distance. Force times distance. Work. Physics. Physics. You apply a force to something over a distance. And who's taken physics? I'm not like calling you out, like you don't remember what work is, but I mean, if you've taken physics, a force applied to something over a distance is going to give you work. That's a definition of work. And so if I have a way of measuring the force at all the different places, then what I'm going to do is find the area, and it will be the total work done. All right? And you can do this for any two quantities. The area can mean something. I mean, physically, it can mean it, financially. Probability and statistics, right? Probability and statistics. If I take, say this is 1. All right, let me try and give you an example you can relate to, I guess. Hold on. Let's say a light bulb. Okay, I get a light bulb out of a box. I'm about to plug it in. The probability that it's going to work when I plug it in, good or bad? Pretty good, right? Brand new out of the box, right? So now is the probability 1 meaning 100%? No. So it's somewhere like that, right? Now, I use it. Over time, right? Here's the probability it is going to work. Probability that it's going to function properly, right? So what should happen is over time, the probability should drop, shouldn't it? Now, it might be linear, it might be nonlinear. It's going to be something, right? Maybe it's a real good probability it's going to work for the first few years, and all of a sudden it starts dropping off. I don't know. Depends on the light bulb They do research on this shit, and they figure out for each bulb what its probability model is. And that's why they'll be happy to guarantee it for the first year, because in all their tests they've shown that 90-something% of them work, so they're okay with refunding you. You know what I'm saying? Okay, so let's talk about this right here. Does that ever cross or touch the x-axis? What's the probability, though? Probability, you brought up a good point. There's a difference between probability and then actual event. So if I get a coin right now, I don't have a coin, but if I get a coin, I flip a coin right now, right? What's the probability that it's heads? There's no probability after the event's occurred. Okay? It's done. There's no talk of probability. It is one or the other. So before I flip the coin, if I say, what's the probability of heads or tails, everyone would say 50-50. I agree with you. Flip it. Now there's no more probability. So probability is only looking at events that have not occurred. You're trying to predict something that hasn't happened. Okay, all right, so I can't talk about the bulb dying ever. So what I can say is that the probability it's going to last 10 years is lower than 1 year, right? Could it last 100 years? That's right. It's asymptotic, right? It is approaching zero. It's like a limit, right? Limit x goes to infinity. The function's going to what? Zero, right? This is going to zero. Never gets there. So, but what we know about probabilities is that the sum of all probabilities has to be 100. It's like when you flip a coin, or not flip a coin. Think about rolling a die, 6-sided die, not one of those fancy board games that have like 20 different sides on it. 6-sided die, right? You could roll a 1, a 2, a 3, a 4, a 5, or a 6. Those are the only possibilities. What's the probability of rolling a 1? 1/6. What's the probability of rolling a 2? 1/6. 3? 1/6. Right? If you add up all these 1/6, 1/6, 1/6, 1/6, all of them together, you get what? 1, right? 6, 6, 1. That's the way all probability models work. So what I need is the area under this curve to be what? The total area under this curve needs to be what? 1. And there are special functions that do behave that way, where you actually have the area under the curve, but the curve goes forever. And you can still talk about its area. So I'm just trying to motivate some of the idea. You've seen probably, maybe, I don't know, a bell curve, right? Y'all ever seen a bell curve? Looks like that. Standard normal curve, that's standard normal curve. That's our bell curve. It has the characteristics that the total area under the entire curve in both directions, and it goes forever, is 1. Right? That's the characteristic of the standard normal bell curve. So in Cal 2, we want to know what those areas are. So what we do, I'm going to have to bring up something here. Bring my Cal 2 stuff in here real fast. I wasn't really prepared to do this, but there we go. Can everyone see this graph okay? Let's say I wanted to approximate the area of that graph underneath it. I want to find the approximate area. Do you agree that I could take a couple of rectangles like that? Now, this area is too much. What I've done is I've cut up this interval into, what, 1, 2, 3, 4, 5 equal sections, right? And when I've done it, I've gone to the right endpoint, I've gone up to the curve, and I've created a rectangle. On the next one, I've gone to the right endpoint, up, rectangle, right? Next one, same thing. What happened here, though, because of the curve, the shape of the curve, this is an overestimate. It's too much area, right? So what I could do is to get rid of all this error, because all that's error up there, right? Error, E-R-R-O-R, right? That's all. This is all too much. What I could do is go with more rectangles, right? Do you see that my error is starting to get smaller and smaller and smaller, right? Smaller and smaller and smaller error, smaller and smaller error. And what is the key, the heart of calculus, is the limit. The limit allows us to let things go to infinity, right? So what I'm going to do in Cal 2 is I'm going to let the number of rectangles go to infinity. And when I do that, I get the true area under the curve. And what you'd have to do, what you probably won't do in your Cal 2 class, and I don't take a lot of time in my class either, is we actually come up with formulas for actually adding these rectangles up. And they're called Riemann sums. It's a real pain in the ass. But to me, it's the geometric idea is the most important thing. Let me back this up for a second, where we had about 5 of them. Okay, that was too much area, right? So instead of going and taking this and looking at the right side and going up, right? Next one, right side going up. What if I did the left side instead? That wouldn't be enough, would it? It'd be too little. But again, if I get more and more rectangles in there, I start to converge to the true answer. Yes? And it does not matter what the function is. I'm changing these functions around right now. All of these I can figure out using that same idea, right? So you get the idea of the Riemann sum? You add them up? Yeah or nay? Okay, so what if I told you now, I know y'all want to get, you got to give me 8 more minutes, please. Okay, what if I told you on that Riemann sum picture that I'm going to take one of those rectangles, okay? Just one of them. And I wanted to look at it over here. The width of it, okay, how wide that rectangle is, I'm going to call that delta x. We use delta whenever we want to talk about a change in x. This delta x is the width of it, right? Of that rectangle. How tall is that rectangle? Well, it's however tall the function is, right? Yes? No, it's the function's height. It's the actual function, right? So that height of this rectangle depends on the function itself. Like if I move this rectangle to the right, the function is going to tell me I'm going to be lower than I was over here, right? You'll follow that? Okay. What happens if I ask you what the area of this is right now? What would you tell me the area of that is? Delta x times f of x, right? Now, what would happen if I wanted you, how could I tell you I want you to add all those rectangles up forever? Like infinitely many of them. Well, I would have to tell you to somehow add them up, right? So I would use this sigma notation, right? Sigma means add them up. And how do I tell you that I want you to have an infinite number of them? Well, I bring in this like limit. I would let like how do I get an infinite number of those? How about if I let delta x go to 0? Wouldn't that make them more and more narrow? So I do something like this. I let delta x go to 0 of this summation. And something miraculous happens. And we're not here to prove it today. But this is the main result of Cal 2. This sum, okay, this sum right here turns into, I mean, there's got to be a number, right, that it adds up to be? It somehow is connected to, believe it or not, the antiderivative. In fact, the notation that you see right here, this sum right here that you see, when we actually let that happen, we have a special symbol for it. It's an elongated S. Okay? Do you recognize f of x as being the integrand? And do you see what happens? We change delta x over to its differential form dx because we've let it become infinitesimally small. And what you get is the integral. The integral is going to somehow become the area underneath the curve. And it's based upon a limit of Riemann sums. What I wanted you to see today is that this right here, okay, this is not just some arbitrary symbol with some crap inside of it. It comes from a summation, okay? It comes from a summation, and it's important, I think, in a Cal 2 class to make the connection visually to this formula and what it means up here. Hopefully your instructor will make that connection because you'll use it throughout the entire semester. This is the area of a rectangle, isn't it? It's the width of it times the height. That's all it is. Add them up forever. That's what this means. Width, height, add forever. Add an infinite number of them up. So I'm sure you want to see it work one time, don't you? Yeah, of course you do. So what if we take this on, but give you an easy one here. You don't need this. Let's say we have the function x cubed. Let's say we want to look at it on the interval 1 to 5. What if I want to know the area there? Okay? I believe it's this one right here. I would like to know the area underneath this curve right here. That's x cubed. That's from 1 to 5. All right? Here's all I have to do to find that area. All I have to do is first find the antiderivative. So I'm going to tell you, I'm going to add up a bunch of crap. What am I going to add up? X cubed dx. Now, I need to let you know that I'm going to be on that interval 1 to 5. So I'm going to go from 1 to 5. All right? First thing I'm going to do is find the antiderivative. What is the antiderivative? 1 over 4x to the 4th. Now, some new notation. We usually put plus c, right? I'll put it in here. We throw that away later, but I don't have time to explain it. Okay, then I'm going to put something here. X equals 1 to x equals 5. This is the big deal. This is what we call the fundamental theorem of calculus, all right? It is the fundamental theorem. It ties the derivative to its antiderivative. The area under this curve, all you have to do is find the antiderivative and evaluate it at those two endpoints. So what I'd like for you to do now is take this antiderivative and please plug 5 in. So what's 5 to the 4th power? Yeah, someone on a calculator get that for me. What's 5 to the 4th? 625 over 4, right? I have 1/4 of that. So 625 over 4 is what I get when I plug in 5, yes? Okay, then fundamental theorem of calculus says this. Subtract from that what you get when you plug in 1. So plug 1 in there, and you just get 1/4. That's 624 divided by 4. What's that? 156. The area under that should be 156. And that's it. Okay? So that is what you're going to spend the first few weeks in Cal 2 finding antiderivatives. It's going to be brutal. I mean, like, surviving the first few weeks, the first test is really, that's where they get you, like, you know, that's where we weed out. Not weed out, but I mean, that's where you separate the people pretty quickly because weed out. Yeah, I mean, but it's not intentional. Yeah, it's not an intentional thing, okay? It's really just, it is a challenge. The material is hard. So, you know, you get through that. After you do that, then you start doing this, and you just say, oh, wait, you know, all I'm doing is plugging stuff in, and it's nice. Yes. What's that? Yeah, what happened to C? So didn't they both have a plus C in them? Plus C, and then this one had a plus C, and then when I subtract them, they go away, right? Like this one had plus C, this one had plus C, so they cancel each other out. You see that? Okay, well, it's come to an end. Unfortunately, we have to stop. So I'll answer your question, both questions you're asking me. Or I don't know if that's both questions, but I have like 80 emails that I don't know. I got real backed up this weekend. I have not touched my computer since like Thursday. My phone kept on lighting up. I just kept, you know, I just forget it. So I've got like 80 or something, probably more than that now. So to answer your question, I don't know. I have not done any bonus on the test. Any of the bonus questions? Or anything, I have not added anything. I haven't graded those. So I will get to it. I don't have any more tests to grade right now, so where the hell's my phone? Oh, there it is. So please just give me some time to get caught up. Crap, man. I have more email now.